have Jeremy Heyl for our CITA seminar from University of British Columbia. Jeremy's had a long career in Canada before he was in the US, at Harvard, at Caltech, PhD at Santa Cruz. Actually, at Harvard, I think he wrote a paper on QED that got me excited that there were people doing QED in astronomy, actually.
This is a bit of the, you'll see the trappings of those results here, believe it or not.
So he's gonna tell us about XP observations of pulsars, and glad to have you.
Thank you. So please, if you want me to go into more detail about anything that shows up, just let me know. Also, as far as with this XP, which I'll explain what it is, most of the large contributions that I've made have to do with observations of the sort of classical accreting X-ray pulsars, meaning, or classical X-ray pulsars. And we'll talk about maybe the most classical one for a good portion of our talk, which is Hercules X1, which, like every prototypical object in astronomy, actually is a little weird, but we'll get into that a little later. But also, anything that is a rotating neutron star, basically, whether it's a classical X-ray pulsar or what used to be called anomalous X-ray pulsars, but now we just call them magnetars. I'm not going to talk about them in my talk, but if you're interested in that, we can definitely dive into that a little bit later. So, X-ray pulsars, but what is XP, right? What is XP in particular? Well, first I'll go in what are X-ray pulsars. Now, we'll go into this. I wasn't that into X-ray pulsars until, basically a few years before XP was launched. A lot of my focus had been on magnetars. And the main thing with X-ray pulsars, compared to the strongly magnetized neutron stars, is they're really, really complicated. And even modeling where the emission is coming from and how it is produced are still right at the forefront of what we can do. So this is just a sort of schematic showing, it's not even a schematic, it's just art by Sasha Mushtakov, who is participant in many of our, contributor to many of the papers. This is for a paper about the first X-ray pulsar to be discovered, and which is Centaurus X3, and also the first one to be observed by XP. Because we'll go into XP a little bit, but the lead of XP is someone who's been involved with X-ray astronomy since the 60s. So he decided on the plan was basically redoing a lot of those first discoveries with this absolutely brand new instrument that gives us new capabilities. So in an X-ray pulsar, the ones that we're really going to be talking about, with the exception of Hercules X1, this is true as well. The companion is a star that's more massive than the neutron star. In the case of Hercules X1, they're actually comparable in mass. That's why it's a little weird. But the key is this star doesn't live terribly long. It's not like we talk about accreting millisecond pulsars or millisecond pulsars, or where you have a neutron star accreting from a low mass star, and it can last a really long time. These systems don't last terribly long, and you're basically accreting often from the wind of this star rather than directly like a Roche lobe overflow. And so we can think about how the X-ray emission gets started in these objects, where it forms. And basically, we think it forms from very close to the surface of the star in an accretion. We need to get rid of that, sorry. Bye-bye. Well, that was no better. there we go, from a hot spot or an accretion column, and I'll talk about what these are a little bit later. But you can see this is just 1, and I think it goes up to 6. So one key thing with these objects is that this isn't drawn to scale, but typically the end of the accretion disk, it gets disrupted by the magnetic field of the neutron star, because these neutron stars are young. They have fields maybe 10 to the 12 Gauss near their surface that we can measure by looking at cyclotron lines. So we know that's what the field is, and that's sufficient to disrupt the accretion disk maybe at 1,000 kilometers or more. So this is clearly not to scale because this is 20 kilometers across. But the key is the accretion flow out here is not hot enough to make X-rays. And basically you have it freely falling down these field lines onto the neutron star. And depending on that boundary layer there, that's where you get the emission, right? It's attached to the neutron star. It's not out here. But in low mass X-ray binaries, you can have the accretion disk almost go down to the surface of the star, and then you get X-ray emission from a whole bunch of different places. But after the X-rays are made, they can reflect off other parts of the neutron star surface. They can reflect off this accretion column. They can reflect off the accretion disk itself, off this stellar wind that's drawn there, or even off the other star over here. So there can be some reprocessing of that radiation. But as we go through the different neutron stars, we'll see that a lot of, at least this part is really, really hard. But when we look at what the neutron stars are doing, what their polarization is doing, it'll tell us that a lot of this isn't terribly important, which is nice, right? And I'll explain why. So when we focus down on the neutron star, we can think of 2 ways that the emission can come from. And this is drawn almost to scale. So the accretion flows down, and it will form a shock here, where it slows down from a good fraction of the speed of light, maybe 30–40% of the speed of light, to, well, again, another good fraction of the speed of light. Maybe it'll slow down by a factor of 3. And then it gets more and more dense as it goes down the column, but it's always flowing down this column. So I've kind of drawn that, and the column is, of course, collimated by the magnetic field. Now, I've shown this in a certain way, which is sort of at the level of what our models are like for these accretion columns. At the bottom, it's sufficiently dense that it's optically thick, and that's basically where the photons are generated by Bremsstrahlung, more or less. And then you have this sort of translucent tube, and the photons bounce around in here many, many, many times before they escape out the side of the tube or the top. And during that bouncing, they get upscattered in energy on average. And this is at the level of, this is a model by Becker and Wolf that basically can account for the emission over a broad range of the X-ray energies for Hercules X1. So, but some key elements that make it different from like the magnetar thing is this is moving. This is flowing down here constantly. So there's a whole lot of thinking about the kinetic effects of the Comptonization. The actual radiation is beamed towards the surface just by Doppler. It escapes out the side, and we developed some models of this. My student and I, Ilaria Chiazzo, which I'll show you some results of that in a little bit. The second idea is if the material can flow out of here quickly enough, it won't form an accretion column. It'll just basically form a sort of lump on the surface of the star. So basically you have the accretion shock down here, and the material up here is not, it flows out of here fast enough that this doesn't grow. And typically this accretion column, if we think about it, I've kind of drawn it wide, but it'll be maybe 100 meters across and maybe 5 kilometers tall. So like if you were to see the neutron star, it's like holding like a lightsaber as it's spinning around, but it's also a gravitationally lensed lightsaber, so it wouldn't look exactly like Star Wars, but it's kind of like crazy to visualize, just the difference of scale, because the neutron star, is maybe 10 kilometers in radius, and it'll have a thing sticking out that's glowing with the X-ray radiation. Now, this we call supercritical, meaning, well, if the accretion rate is fast enough, we're in this situation, and this is subcritical. It's unclear whether we've seen any particular objects in this state versus that state right now, right? Where that's the level of how rudimentary, right, the modeling is. This actually, we can account for the spectra from these objects. This one, although it seems, oh look, it's sort of like a neutron star atmosphere, and we know how to do that, right? But it's very, very hot. So if you were to, and we tried, right? If you were to pretend this is a neutron star atmosphere and try to calculate it, you'll find it just blows itself apart. There's no way for it to converge. And the simple way to get it to converge, which may be physically meaningful, is to just increase the surface gravity of the gas. It's not like really increasing the surface gravity of the star, but if you think about it, that's kind of a heuristic way to think about the fact that this gas is falling down at a good fraction of the speed of light and is suddenly decelerated. So from the frame of the gas, it really feels like it's being decelerated. So in the frame of the gas, there is a large effective gravitational force.
Should these be helices rather than straight field lines?
Sure, but we're not, there are people who try to put all this together, and it's really, really hard. So there are models like Omer Blaze and a student are now working on this sort of picture, and with MHD and some prescription for the rate of transfer. The key is that in this column, the cross sections for scattering and so on are, well, it's really only scattering in the column that we're worried about, are very energy dependent. They depend on polarization, and they're strongly dependent on direction as well. So it's a really tough problem. And like I said, it's moving at a good fraction of the speed of light as well. So it's hard, right? So, pardon me?
Can I ask a question?
Yeah.
Sorry. So I'm curious, like, is the X-ray emission as a function of the distance between the star?
Oh, you mean along this column?
Yeah.
Yeah, so in the models, in the sort of original models that's set out by Becker and Wolf, they kind of just do it in bulk, but I can get into a picture. It is a function of, along the column, there'll be more emission near the top than near the bottom. Because if you think about it, up here it's more dense. Up there it's less dense because it's slowing down as it goes down here. So the density is increasing, which means, like, if we think about this, it's really like a light, it's a translucent thing, like a cloud. And up here, the mean free path to escape the cloud is larger than down here. So you're getting photons from a larger region are able to escape at the top than the bottom. The top is brighter than the bottom. But in these models, the temperature is the same everywhere and stuff like that. It's nothing super sophisticated, right? It's so Ilaria and I developed some models where we're looking. This is at Hercules X1, and basically this is the pulse profile of Hercules X1 during a particular. We'll get into Hercules X1. It does all sorts of weird and wonderful things, but this is during a certain part of its cycle where it's the brightest, right? So this idea of this accretion column can make a really nice, strong, sharp pulse, which is what we were focusing on. And then over here, which is a cute thing, is once you set up this picture and you pick some angles that explain this, you can ask, what is the observed cyclotron energy, right? And the reason why it shifts up and down is because at different stages of as the star is spinning, you're seeing emission up here or down there. We don't really assume that the field is weaker up here than down here. The key why the line moves is this material is moving at a different velocity than down here. So it's just a special relativistic thing. So, we weren't trying to fit that, but you can see, like, heuristically, it kind of looks right. So that's great. And then one can go on and ask,
what gives you the peak in brightness? Is it which way do you have to be looking at?
This one is like, I'm pretty sure, like, if when we're looking at it, this is when that lightsaber is actually pointing away from it, more or less, because just of the gravitational lensing, you get a huge magnification of it.
And it's boosted.
And it's also boosted, right? Because you also have to worry about, in these calculations, which is amusing, is a lot of the photons hit the surface. In this picture, they don't. In this picture, a lot of them hit the surface. We didn't worry about them reflecting. We just said if they hit the surface, they're gone. And then so if you put this thing away from you, the radiation comes out the side and gets gravitationally lensed to you. So yeah, the typical, it's not like most, you think gravitational lensing, it's like arc seconds. No, this is radians of gravitational lensing that happens. So it's kind of, that's when it's brightest, which seems weird. I mean, for various reasons, this model that we have is completely excluded, but so too is every other model. So it's all good, but we'll see why it's excluded in a little bit, which is why we built the telescope, which is wonderful. So this is one of those wonderful things where, you're proven wrong within like months. Nice, exactly. But it was the best that anyone could do at the time, and it's the best that anyone had done for about 30 years. No one had worked in this area at all. So the key thing to take from this is, this is just different energies. XB observes in here. The polarized fraction is somewhere 70%, right? And it's specifically in the mode where the polarization is parallel to the field, just like what I've drawn here. That's the sort of the so-called O mode. But the key is it's very polarized. Okay? So, well, let's build it. Build some instrument to measure this. So this is artistic rendition of XP. It has 3 X-ray telescopes and then 3 detectors down here that basically run in parallel. This is an extended optical bench. It was launched on a Falcon 9. And what's kind of funny about it is this collapses. So it's sort of like when it's collapsed, it's kind of maybe twice as big as this. It's not very big. And of course, it's SpaceX. So you have videos on everything. And you can watch the video of this tiny little satellite in the giant fairing because it goes into an equatorial orbit. So launching it from Cape Canaveral has a lot of delta V, and it was just, SpaceX wanted to see whether they could do it, and they would do it cheaper than, it was supposed to go on a Pegasus, which is this sort of modified cruise missile, which forced it to be really small. And then SpaceX says, we can do it for cheaper, we'll give you a cool movie, and it was beautiful. It was launched 2 weeks before JWST. So we had a lovely movie of it floating off, higher production value than the JWST movies because the SpaceX has a lovely cameras. Also, if you're interested, you can, of course, they have cameras on the bell of the rocket, which is really fun to watch because, of course, the satellite has to take this sharp left turn to get into the equatorial orbit. You know, it launches, and then it sits for like 15 minutes, and then it starts again, and it's like, and you can see the Earth turning behind, because it doesn't, the burn is like 2 minutes. It's really quite short, and you can just watch it. And then once you see, oh, it stopped, like, oh my gosh. So this mission had been in the works for about 20 years. And the lead on the mission, as I mentioned, was, and we'll get into him again, is someone named Martin Weisskopf. And Martin was, I don't know if we'll see pictures of him, but he was involved with Uhuru. He was working with Giacconi, and back in the early days of X-ray astronomy. He was also like the project scientist of Chandra. And this had been something he had been hammering on. The last X-ray polarimeter was a thing called OSO-8. It observed or detected polarization from precisely one object, the crab, in the late 70s. So this is 2021, so 40 years later, no X-ray polarization measured from anything. So as I've said to people before, it's like being Galileo, literally being on this mission. Like, you have no idea what you're going to see. And of course, you very rarely see what you expect, which is also wonderful. So what's the enabling technology of this, this telescope, right? So I talked about, well, it's this X-ray mirrors up here. They're not doing anything to do with polarization. It's the detector at the bottom, which is quite fun. So usually in X-ray astronomy, when you detect the X-ray photon, it will hit something like a CCD, and you will read out the CCD periodically with Chandra. It's like every few seconds, I think, unless you really want to do it faster. And you'll measure how much electron charge accumulated in each little pocket of the CCD, and that tells you the energy of the photon. That is, so, you know, every couple seconds you get an image with that you interpret as the energies of the photons that have arrived in that interval. This is not how this works. So this is what we get for a single photon from this instrument. We get the entire track, and I'll explain what that is, with how much charge has arrived everywhere, when these things were measured, and when the event occurred. So basically a photon comes in, and it goes into a gas here, dimethyl ether, and the photon will ionize an atom in that gas, and that electron will fly out, as we see here, right? And that electron will ionize other particles along the way as it travels along, and then those charges will, and there's a little bit of a voltage here. They end up on this metal plate down here, which is has lots of little holes in it that are about the size of these pads down here that detect the electrons. So this plate, when the electron comes in, a single electron will get multiplied by many, like maybe 2 orders of magnitude, and then we count them as they land here. So what we see is sort of this shape where we can infer where the photon hit. So naively you would say, oh, the photon hit over here where there's lots of charge, but that's the opposite. So where the electron is moving the slowest, sort of at the end of its track, is where you have the most charge. So, and of course, during its motion, it can change direction. So you can infer sort of from the opposite end of this maximum that the electron started over here, and then we're looking at the direction that it goes, which is correlated with the polarization of the photon. It isn't, it has a sort of cosine squared dependence. So it goes this way, it doesn't mean, that means it's more likely to be polarized like this. There's even a chance that it's polarized like this. The detector is not completely 100% sensitive, but it is, you know, it's more likely with this polarization if the electron is gone like that. Since we get so much data on each photon, we also get its energy, we get where it hit on the sky at sort of XMM resolution or a little bit better, we get when it arrived to microseconds. So it's like quite a bit different than a lot of X-ray astronomy. Each photon carries a huge amount of information. The energy resolution is about maybe 1/10 of a keV, so it's pretty good. Any questions so far about this? Okay. Yeah, so it's like, that maybe that's too much instrument-y. But yes.
A quick question. So what happens when you get multiple photon detections at the same time?
You know, if we were only so lucky. That's what I say to that. So the instrument, if you remember, it's about this big. Its collecting area is on the order of, you know, tens of square centimeters. So the dead time on this isn't terribly long. So, you know, okay, you need to get many photons. You know, I think the dead time is of order milliseconds, and we're never at count rates of kilohertz. Okay, so we're okay. I would love it if we had that problem. That would be awesome, but we don't have that problem. Okay, so the Pulsar Zoo. So, as I mentioned earlier, well, this is a small telescope. And typically, because of how we are measuring X-ray polarization, basically to measure the polarization, we have to take how many photons or how many electrons lined up this way minus how many electrons lined up that way. So I'm taking the difference of numbers, but also it's not 100% sensitive, right? So you need a lot of photons to get a signal, right? Because although, okay, we have a million, a lot like millions, like 1 million is a good number, right? And, whoops. That's this one, sorry. So a lot of the sources that we look at, especially if we want to get, of course, none of them have been looked at before. So we just start with the very bright X-ray sources, which is wonderful and fun because we're seeing something new, what's going on. So I'm just going to go through a bunch of the X-ray pulsars, sort of in the order of the observation. So the first one we looked at there was one that we looked at during commissioning. I don't know why we picked it, but it was so short we didn't really see anything at all, which was SMCX1. But I think we revisited that later, but this was the first one that was observed officially. Of course, the first light image of this telescope was, I'll think of Chandra, not the crowd, Cassay, right? That was also the first light of Chandra because it's the same guy, right? So here's Centaurus X3. A few things like, there's 100 dots here per period, and it's just repeated. you can see it's around 20,000. So 2 million photons, that's the round number that we're talking about to get interesting stuff out of it.
And the counting is like per second or?
Yeah, well, I mean, I have one, like a really bright source we'll talk about, where the polarized flux was even per second, which is nice. But that was we got like 10 million photons for that.
These are megasecond looks typically.
For like these guys can be, yeah, well, they maybe 100 kiloseconds. For the magnetars, because they're fainter, are megaseconds. We did look at SCO-X1 because clearly it won't destroy our instrument, but we didn't see anything. I mean, I think it was polarized, but we didn't see anything like the spin period or anything like that. Okay, so let's just go through this. So this is the pulse of Centaurus X3. It looks like, hey, it looks like a pulsar. It has a big pulse, and then it has this little thing here, and then it gets fainter there. The pulse fraction is quite good, quite large. Then there's this middle plot which shows the polarization degree as a function of phase. Is it 80%? No, it's like around 10%, right? And this is what we found consistently. What does it mean? Well, that's the drawing board over here, and I'm not really going to talk about that. Like, there are different interpretations from this, but also the models that we have, I mean, it's really hard, and they're not at the level of realism that we have in neutron star atmospheres. So I wouldn't necessarily, I mean, of course, I was part of some of them, but they're sort of educated guesses. So the fact that it's 8 versus 80% could be just with how we treated how photons escape from the column, which was very heuristic, and things like that. So the other thing that's kind of interesting, and we'll see this, is, okay, this looks good. We can look at what the polarization angle looks like on the sky. And it basically always follows a sort of well-behaved quasi-sinusoidal thing. I mean, this point is maybe exceptional, but you do expect things to be off a little bit occasionally.
That's not aligned with the flux peak, right?
In this case, I mean, yeah, so in this one I've drawn the flux peak maybe in a weird place.
Yeah.
It's this part where it is, right?
Yeah.
But I'm going to talk about a little later why they all end up looking like this, and what that is telling us. It doesn't tell us that much about the emission, but that also makes it easy to interpret. So this one is another one. It doesn't look so well behaved. It kind of goes up, and then it goes down, and then it looks like it's going to go up. It goes up here, and then it has a huge in the middle where it's cut out. And then, it does it again. The polarization degree is again about 8%. And when you look at it, you can fit it with, again, this, it looks weird like it's jumping, but you have to realize this wraps around to this. So basically, the polarization is doing something like this on the sky. But it's definitely like something is more complicated in this source. My feeling on it is that the accretion flow itself blocks our view of the spot as the star is rotating, which is why we get sort of a dip right in the middle of the highest part of the spectrum. Also, the polarization is highest there as well. But so that one, it has a sort of, and okay, it goes up and down. It has this extra little bit. It's basically looking okay. Now here's Vela X1. I mean, I don't know what that means. If you want to interpret that, I mean, what is it? Is there lots of flow onto the star in different places? Are we seeing the flow here, and then when it hits, and maybe when it takes a turn, or are there tons of spots like the flow is going?
Are these curve steady, like you revisit the source to get the same?
Depends on the source. These guys, yes, but I'll go through ones. The more interesting ones are where these things, which I'll talk about in more detail, where things are changing with time. A lot of them, so I'll talk a bit about that a little later. This one again is 8%. That's maybe the key lesson, like it's always low. And despite this thing looking really weird, and you'd be like, okay, I mean, fair point, you go, well, this is off by this amount. That's weird, but how far it's off is 90 degrees. So during this phase here, instead of emitting in one of the polarization modes, it's in the other. But it's still, when you kind of look where the polarization is, it's basically doing this. And sometimes you're looking at this finger, sometimes you're looking at the thumb, but it's basically just rocking back and forth. Even though this would tell us the magnetic field, oh my God, it's going to be so complicated, what's going on, but it just goes. Okay. And if you want to learn more, those are the phone numbers of these 3 papers. There's going to be more. I'm going to, of course, it's a zoo. It has to have, huh?
He was like younger.
Of the X-ray pulsars. Yeah, I don't know. But yeah, that might be why it's doing this.
It's a little slower.
Yeah, I mean, I have one that's like 200 seconds that will talk.
Maybe.
Well, no, later on, I have one that's 200 seconds.
Sometimes it speaks like 4 seconds or so.
Yeah. This one I forgot. The ones I'm going to talk about a lot towards the end are this one, LSV, which is around 200 seconds, and Hercules X1, which is about 1.24 seconds. So here's another one, X Percy. It again, polarization right around 8%. It just seems to be like where it wants to be. Its profile also has this really sharp cuts. Maybe there's some absorption there. And if you look at the polarization degree, it's basically just going around like that. So nothing very complicated. Here's one with, again, a kind of funny, pulse profile. Like, would anyone have ordered that? It's almost like Vela. What do all those different components mean? Different magnetic field regions on the star, I don't know. Polarization degree at the few percent. Here there's a couple solutions that are kind of, which are all drawn here because they're sort of equally likely. So one is one where it kind of is just going, it kind of goes like almost all the way around and then back again, which is sort of degenerate with one where it goes around. Because they're almost the same, because it doesn't matter where my finger points, it matters like where both of them are pointing, because the polarization isn't a 360 degree thing, it's just 180. And here's another one. Again, you can see the story, polarization much lower than expected, complicated pulse profile, polarization angle, quite simple with what it does. So why do things, like how polarized it is, we obviously got our model wrong, because the models were saying 80% or whatever. So this part was wrong, but in our models, this part, the angles were basically, we were getting them right. And why is that? And there's a sort of deep reason for that. And it's something called vacuum birefringence, which is going to make Bart happy, I hope. So back in the 30s, these 3 people, not him, that's the wrong Euler, but that's Euler's just ancestor. This is Euler the mathematician. He had a descendant, Euler the physicist, named Hans Euler. Heisenberg, who's not this Heisenberg, but this Heisenberg, quantum mechanics fame. I have a feeling in other audiences, this is the more famous Heisenberg equation. You haven't?
No.
Oh, but a lot of you chuckled, so you know exactly what that
He
is.
does some good work.
Huh?
He does some good
He
work.
does some good work on the
He's a chemist.
He's a chemist. But what is his name? What is his name? Yes, but he goes by Heisenberg, right? And then finally, what's interesting is Weisskopf is not the lead of the mission Weisskopf, but his uncle, Victor Weisskopf. So they're all related, which is fun, except for Heisenberg, right? That was just sitting there, it had to be done. So this is in the 30s, sort of just after the Dirac equation was written down, and they asked this question where if we imagine we have the Dirac equation for an electron, and there was this picture of all of these states, if you remember, this is before quantum field theory was well formulated, and they imagined all these negative energy states were filled up with particles. Pardon?
Electrons.
They were filled up with electrons, and if you lifted one up, the whole would be a positron, you can remember. But that was the picture that they had. And they went and said, oh, let's imagine there's this infinite sea of filled levels down there, and we're going to apply an electromagnetic field. How does the energy of those infinite sea of electrons change? And of course, you get a number that's infinite, but they said to themselves, my uncle, my granddad was Euler, I can handle these infinities, and Heisenberg was Heisenberg. And basically they realized that a lot of that infinity, that the answer would be infinite when you applied no field whatsoever. So you knew you could subtract that away. Like, what's the sum total of all the energies of these electrons? Okay, I can just subtract that away. It's the difference I'm interested in. Of course, it was still infinite. And then they realized, oh, well, part of that infinite is proportional to this term. And they said, oh, well, that's just the definition of these things. So they dropped that, and they get a finite number, which is this horrible expression. Okay, and I put it up in the German, right, because it's just fun and the letters are curly and stuff. But basically this means critical field, and if you plug in numbers here, what is it? It's 4.4 times 10 to the 13 Gauss. It's this sort of characteristic field where things get really weird. But if we look at this expression, this part is just normal electromagnetism, and you can see things are proportional to quadratics of the field. So if you were to ask, well, how fast does a photon move? This part will give you things that are like the speed of light regardless. Over here you can see it's a function. We can write it in this way. There are other ways to write it where the integral isn't infinite and stuff. You can regularize it a bit. But the key is this is a more complicated function of fields. So if you were to expand this out in terms of fields, you'll get terms like E times B squared. You'll get terms like B to the fourth, E to the fourth, and stuff like that. And so what that means is that if you have a magnetic field out there, and you have an electromagnetic wave passing through the magnetic field, how fast it moves depends on its geometric relationship to the magnetic field. Like, so if the magnetic field points along the magnetic field of the wave, obviously that's going to contribute to B squared differently than if it's perpendicular, or B cubed, and so on. So if you look at this equation really closely, you find even if the field is, we can go through it. If the field is of order the critical field, what you find is that photons go about 1,000th less than the speed of light. And it depends on the polarization of the photon. So if the photon's electric field is wiggling in the same direction as the magnetic field, it goes a little slower. And if it's going in the opposite direction, it always goes slower than the speed of light. But out of the two, it goes a little faster. But it's a very small effect, and it goes as field squared. So I said 10 to the 14 Gauss, it's of order 1,000th. At 10 to the 12 Gauss, it'll be order of 100,000 difference. So if we're looking at the neutron star, what is that going to do for our observations, right? Well, if you calculate, of course, that's the field near the surface. It diminishes as you go away. So one polarization will lag the other by like nanoseconds or microseconds. So clearly that's not observable, right? But there's something else that happens, because that's not the quantity of interest. It's how much the time is different between the polarizations compared to the period of the light, which clearly for X-rays, it's really large. So one polarization lags relative to another polarization by millions of wavelengths or more. So what does that do to the light? So here's what it does to the light. And this is a piece of technology that many of you spend days staring at, or most of your days staring at, which is an LCD screen, right? So does anyone know how it works? There's this LC in LCD, which stands for, actually we're running low on time. But basically what happens is you have a birefringent material in the middle, and that twists the polarization from this direction to this direction because the birefringent material twists very slowly. So what's happening in the neutron star is as the light leaves the surface, this is the polarization that you would see at the surface. It propagates a long distance away from the star, and the polarization, that is symbolizing like the one loop correction of QED. The polarization vectors end up lining up. In this case, I've drawn it so it's perpendicular to the projected axis of the magnetic field in the star. So even if the field is much more complicated at the surface, this final state of the polarization occurs at tens or hundreds of stellar radii, where the field is lined up quite nicely over where we're observing the photons, either perpendicular to the local, to the projection of the magnetic axis on the sky, which would be the X polarization, or parallel to it. So this model where the polarization just follows the projection of the magnetic field vector on the sky, not the field vector, but the dipole moment vector on the sky, is imaginally called the rotating vector model. Because all it is what a rotating vector looks like from your point of view. So I'm going to skip ahead to Hercules X1. I'm going to skip this guy. He's interesting, but less. So Hercules X1, I guess I have about 10 minutes, was discovered in the early 70s with Uhuru. This is Bruno Rossi. This is the telescope, about the same size as XB, more or less. This is Marjorie Townsend, who led the launch team. It's immediately obvious when the data came down, that you had a source whose period was about 1.2 seconds. It was the second of the X-ray pulsars to be discovered. But over the next, more or less year, or no, that's the same observation, they found that the period varied on a 1.3 day or 4 day, and that's the orbital period of this around its star. On top of that, there's another thing where it turns on and off every 35 days. It does a cycle of being brighter and fainter every 35 days, which we can see here. These gaps are when the eclipses are. And you can see there's a stage where it's brighter, which is called the main on, and a stage where it's fainter, and then there's a time where we don't see it at all, or very faintly. And this is ascribed to a warp in the accretion disk that is blocking our view of the surface of the star. But it's been 35 days in period, essentially for 50 years. It's incredibly stable. So where did that come from? So we looked at this with XB. We had observations not long after launch, like 3 months later, and then again a year later. So what's shown here is the XB flux in gray. This is just the RXTE flux, I guess, just a heuristic to show you. And we observed it in the short on and the main on in 2023, and in the main on, the brighter stage, in 2022. So from the 2022 observations, we found what was the direction of the projection of the spin axis of the neutron star on the sky, which we can fit with this rotating vector model. And we found that it's not aligned with the orbit, with the star. So the angular momentum of the orbit is different than the angular momentum of the neutron star, which is important in what follows. So that one observation told us that. It was also not very polarized, typically again at this 10% level. In the main on, it looks like a respectful pulsar. It has a nice pulse. In the short on, depending on exactly when you see it, it's much less pulsed. You can see it at other parts of the short on, and it looks a little bit more pulsy, but it's quite a bit different. The polarization during the short on is about twice as big as during the main on, which is interesting, but the flux is 10 times lower. Okay, but what's interesting, we looked at the 3 observations here, and we can fit them all with these rotating vector models. So the first observation, I have to visualize where these all are, is best fit by this red curve. And then the next main on, you can see, which is a year later, the polarization has gone down a bit. The angle has changed by about 10 degrees, the mean angle of that polarization. And the second thing to notice is during the short on, the polarization direction varies by a lot less than during the main on. So these are the sort of 3 key pieces of information that we can get out of this. And then what does that tell us? So these are just the numbers, but basically these different numbers that we want to focus on are theta, which is the angle between the rotation axis and the magnetic pole, which during the main on is about 16 degrees, and during the short on it's much less. And the other number is where does the spin axis, where is it on the sky? And it went from somewhere in the 50 degrees down, so like around 58, down to around 46. So it also changed. So what's going on here? So the basic idea, which is kind of neat, is that, Hercules X1 isn't round, right? And what's happening is that as it's rotating, the spin axis isn't on the symmetry axis of the neutron star. So the spin axis drifts through the crust of the neutron star, and sometimes the spin axis is very close to the magnetic axis, so you get a very small variation in the polarization direction, and sometimes it's quite far, and you get a large variation. And you can go to yourself, well, the spin period is 1.24 seconds, and this happens on 35 days. That's 4 times 10 to the minus 7 is the oblateness or the eccentricity of the crust of the neutron star, right? So the important thing, and you can also see this in the data, is I have 2 potential neutron stars here. And maybe not everyone can see on the floor, but you people in front, this is one neutron star, and I spun it, and here's the other neutron star. So what's different about those?
Hard-boiled.
One's a hard-boiled neutron star, which is this one, and this is a raw neutron star. So what do you think Hercules X1 is? Is it a raw neutron star or hard-boiled? It's a raw neutron star. So the key is this egg does not rotate as a rigid body, and neither does this guy, which is, this makes, because first of all, we have this upsetting thing of free precession, which upsets everybody. It's actually likely to be triaxial free precession, which upsets people more, but it's not completely free, there's torques, and I'll show you about the torques in a second. Exactly. But it's, we have a misaligned accretion disk, which is what the first observations tell us. So the key is I could spin the hard-boiled egg and spin it not about its axis of symmetry, and it would freely precess. This is actually the law. I can feel it, right? The raw egg, if I spin it off its axis of symmetry, because the thing inside, the liquid, is not rigid. It only wants to rotate about its axis of symmetry. That will damp this free precession in order of 100 years. There is torques between the crust and the inside, which makes, in this case, wonderful. So we look at this and, okay, free precession, great. But then astronomer or anyone says, well, it's soft egg, or raw egg, not hard-boiled egg, because they had talked about free precessions in pulsars, and everyone's like, oh, it's a raw egg. That precession will die out very quickly. But this is not a radial pulsar. It's an accreting neutron star with a misaligned disk. And we know it's misaligned for several reasons, from the polarization, also because the disk blocks it every 35 days. So if we look at it closely, and just to focus on the free precession to start with, we can think about different possibilities of once you're doing free precession, you end up with tons of angles, which I've just drawn here. These are the Euler. Oh my God, we're back to Euler again. Oh, how did that happen? And there were models for this free precession that were presented where the free precession itself was explaining how the pulse profiles were changing, and that required these angles to be really quite large, like the free precession to be large. That's not what I'm claiming here. The free precession itself only provides, it's the conductor for the disk, and we'll see why that is in just a moment. So either a model like this or a model like this, what this is showing is this is a model where the neutron star is, and we can figure out whether it's oblate or prolate. I'm pretty sure it's prolate, but I'm not 100% sure. If you watch very carefully, you can discern those two, but here it's just prolate. So this is the misalignment angle. So this is basically how far away the spin axis is from the symmetry axis. And if it's prolate or oblate, that's constant. This one is triaxial, these ones. And for some subtle reasons that I'll go through, this seems to fit a little bit better. But it's wonderful. It's like breaking out Goldstein. Got to throw in the Euler angles. It's wonderful. But the second thing we noticed was that the angle of the spin axis moved on the sky over the course of a year, which tells me that the crust, the key thing is, what I'm doing now is my experiment is I've drawn an X on the surface of this egg, and from 2.5 kiloparsecs, I'm watching where that X moves across the sky. I'm only looking at the crust. What I'm not able to measure in the inside. So basically, if I look, the angular momentum or the spin axis of the crust has shifted by about 9 degrees over the course of a year. And if I ask what torque that is, given the sort of canonical neutron star mode of inertia, it's this number, 3 times 10 to the 37.
You're gonna start first though, with inertia.
getting there and building it up.
Well,
That's
you
the-
do it in units of 10 to the 43, that's
That's the total star, I think.
45.
Oh, maybe I should put 45. Yeah, this is too big to be the total whole star, right? So what I mean is if I'm torquing the entire star, let's say this is the whole star, to get rid of that, we'll pretend whole star. The crust, the accretion torques fall short of this by a factor of 10 or so. There are two types of accretion torques. When I was initially thinking about this, I'm like thinking of the spin-up torque, but that's not what's important because it's misaligned. Did I say it was misaligned before? It's misaligned. So this is the misalignment angle here. So what happens is basically you have this magnetic field from the star is, of course, it disrupts the disk at some point, but beyond that, it's still dragging through the disk. And if it's misaligned with the disk, there's torques. So one torque is a precessional torque, which is what we want. That's going to drive the precession of the neutron star. It will also drive the disk to precess because, of course, it is a little bit of an open system because there's also the inside of the neutron star. So this is what's driving the disk to precess, but it's also driving the neutron star to precess. So this guy drives the free precession. If this were to shut off, the neutron star, the precession, free precession will dampen. The second one is the warp, which you can see that also depends on the angle between the magnetic direction, the magnetic axis of the star and its spin axis, which varies on a 35-day time scale. So quite naturally, we're going to drive a warp also on that 35-day time scale. So the important thing is that these numbers, if we think about the moment of inertia of the crust, these numbers are typically about 10 times what's required to do this to the crust. So that's overabundant, but that's okay because the crust is feeling a torque from the disk. It's also feeling a torque because it's a raw egg neutron star, not a hard-boiled neutron star. So what we actually see this is just the difference between the torque exerted by the disk and the torque exerted by the interior. And if we get it like even more physical, it's the difference between the current accretion rate and the average accretion rate over the last 100 years or so. So you could even have, if like the accretion rate changes, this direction could completely turn around. There's nothing sacrosanct of it, right? So it's really, I think it's quite amazing. We've had further observations and it keeps moving. We've had further observations of the short on where it has a nice pulse, like a more dramatic pulse, because at different stages of the short on, the pulse evolves, but still the angle is very small, the angle between the field and the spin axis, which is what you would expect from this plot, right? The angle remains small, or the extent of how the polarization shifts remains small for a large fraction of the percent. So finally, just one thing that I was surprised that you could calculate this, but it's kind of neat. So if you have the Euler equations and you solve them, whether it's triaxial or not, you can ask the question, if I'm watching the little cross go around the star, how much time does it take to come back to where it started from my point of view, which is what we call the period of the neutron star. But in fact, the period isn't constant as you're precessing, which is not something I really appreciated before. So the same group that had proposed these models did this calculation where they took, of course, people are always looking at Hercules X1, they measured the spin, and of course Hercules X1 is spinning up and spinning down on a long time scale based on its accretion rate right now. You subtract that out and you kind of flatten it. And maybe with some imagination, or maybe not, this is not a fit. This is just, given the models that I showed you earlier, this is triaxial, showing how the period that you would measure it at an instant varies with time compared to, some mean period. You can see the units are microhertz, but it's quite useful because this sky is super bright and it's detected with Fermi gamma ray burst monitor. So you know what its period is whenever it's in the brighter stage. So, this gives a hint, maybe it's triaxial even. There would be no reason, like if it's already asymmetric, why wouldn't it be triaxial? Other things are like if we had fast spinning neutron stars who were this asymmetric, they're on the verge of being detectable with LIGO. So it's just right there on the limit. But this guy is accreting. There could be lots of reasons why the crust is asymmetric. It doesn't matter what's inside. All we're looking at is really the crust. So I'm going to leave it at that. It went maybe 5 minutes long. We started late. I hope thank you for your attention and your indulgence. Any questions or discussion?
None online.
None online. Yeah.
So you said there's a torque from the interior to the exterior, which you now know, I guess.
Well, I know, I sort of know. I mean, I guess I could work out, like, I know if I knew the accretion torque precisely, which I don't know.
But I thought it was only a tenth of the.
Yeah, so it's certainly of the same order then, right?
Oh, no, the two, like, so this number here is going to be of the same order as the torque between the surface and the inside. Yeah, they have to be similar because they're only off by 10% relative to each other. If they were exactly the same, then this wouldn't happen, right? But like this is just heuristic, right? What's the inner edge of the disk, right? It's just sort of showing where it is. Now, if you can ask, right, so given that it's liquid inside and let's say you trust the calculations of, it's a superfluid, there's vortex unpinning, there's yada, yada,
That's what I was gonna
yada.
ask about.
So there's a lovely paper by Ali Alpar, who's the usual, I forget who the other one was, in the 80s, that goes through all these arguments and basically, it was a perfect framework that we saw here. So one can ask, and they of course give numbers, like how much torque you need to have it misaligned by how many degrees and stuff like that. I haven't put that together, but of course everything has like factors like this. So I'm pretty sure it can work. The key is larger torques are required to make it more misaligned. And it's sort of also just me kind of getting through the innards of that paper to understand exactly everything that's going on. But I mean, the physics is the same as this. It's just, more complicated because it's a superfluid and stuff. So like, I know it's gonna depend on this misalignment in a nice way, right? Larger, and so I know I can reach an equilibrium at some place. So if I trust that interior physics, then I could tell you, oh, this is the torque that's required to keep it in this state, and then take it off by 10%, and then I know this one.
Right.
Yeah.
So there are quite a few other X-ray binaries which have these sort of superorbital periods.
Yes.
As there are cataclysmic variables, right? This is probably maybe not the answer, or do you think those are all also
I don't
persisting?
know. If it's a white dwarf, is it going to freely precess? I don't think so, although the inside could be solid, so maybe it could, I don't know. It's the opposite of the neutron star.
Right.
It's solid on the inside, it's soft on the outside. I think Centaurus X3, it's just they're very, I would love to look at the other ones. It's just quite costly, right?
Yeah, and it's mostly the Magellanic Cloud ones, SMCX1 and LCX4, I think, that have the.
That do that, I think, and
Maybe
yeah.
CX3 too, I'm not sure.
I think Centaurus X3 might too. It's just this guy, this is like the poster child. So, we want more Hercules X one time. They're like, sure. So Hercules X1 shows other oddnesses, which is part of why this clock, I think, is important. Sometimes it just turns off entirely from our point of view. Like you don't see it, like it misses a few cycles. And then it turns back on again, and it's right on step. Now, is the accretion disk on? Probably not. Is it that it's blocking entirely? Maybe. But it's sort of like the accretion disk is in a much different state, but it still keeps time. And what's kind of maybe amusing is if you look at this keeping going, it looks like it might have a period of several years, meaning like there's the precession of the spin axis relative to the sky, like the Earth's precession of the equinox. This free precession on the Earth is called the Chandler wobble. And its amplitude is like 100 meters. I have a good story about that, but if we have time, I'll tell that story. Whereas here, it's like, it would be equivalent of thousands of kilometers, right? Because of course, there's a big torque on this guy, and not such a big torque on the Earth. But I suspect if there were no torques on the Earth, there'd be no Chandler wobble. Other questions? So I can tell you the Chandler wobble story, like where I learned about the Chandler wobble.
I think we should go up.
So is that what we do? We go up and have.
Yes.
Well, this Chandler, well, I can tell it upstairs.
Tell it upstairs, there's coffee and refreshments.
All right.
Thank you. Safe for the whole phone.